Hello, I'm Álvaro Calafell, and this is the fifth part about the impact of harmonics in electrical installations. In this part, I will explain the impact of harmonics on uninterruptible power supplies, UPSs, and motors. In the last video, we studied the impact of harmonics in different electrical components. In this video, the effect on UPSs and motors will be explained. Harmonics may produce two effects in UPSs. The first relates to the design. In particular, the determination of the nominal power of these UPSs that feed system equipment. If the UPS feeds a linear load, the nominal power of this UPS will be calculated from the supply voltage and the root mean square value of the current consumed by this linear load. However, if the UPS feeds a nonlinear load, the current drawn by these nonlinear loads may have a high crest factor. A UPS sized considering exclusively the root mean square value of the current may not be capable of supplying the necessary peak current and may be overloaded. For this reason, the nominal power of UPSs supplying nonlinear loads must be calculated from the peak value of the currents consumed by the nonlinear loads divided by the square root of 2. The second impact of harmonics on UPSs is related to the resonance phenomenon. If a capacitor bank is connected in an electrical installation to compensate reactive power, we know from the first video, Impact of Harmonics, that the resonance phenomenon between the reactance of the grid and the reactance of the capacitor may appear. This is similar in the case of the UPS, but the short-circuit power of the UPS is much smaller than the short-circuit power of the grid, and the resonance may be produced at lower harmonics, where the harmonic currents injected by the nonlinear loads are higher. This can produce high harmonic voltage distortions at the UPS terminals. Harmonics produce two effects on motors. The first being oscillating torques, which can produce noise and reduction of the motor's average life. We can observe that the mean value of the torque is not affected by harmonics, but oscillations around the mean value are produced. The second is an increase in the motor power losses. These harmonic power losses can be related to the fundamental power losses with the expression shown below. As an example, imagine a motor fed with a supply voltage which contains the harmonic distortions in the table. Considering a machine constant of 30 and applying the previous expression, we can observe that the harmonics increase the power losses with respect to the fundamental at 10%. Hello, this is Álvaro Calafell, and this is the last part about the impact of harmonics on electrical systems. In this part, I will explain the impact of harmonics on electronic equipment and flicker. Previously, we spoke about the impact of harmonics in several devices, and this last video will present the impact on electronic equipment and the influence on flicker. With regards to the electronic equipment, the impact of harmonics is summarized in the following issues. Harmonics can produce the maloperation of power electronic equipment because they can shift supply voltage zero crossings. They can also produce malfunctioning and shutting down of computers and other electronic equipment because this equipment is very sensitive to voltage distortion. Moreover, harmonics can also produce light variation and oscillations in the picture and luminosity of TVs and computer screeners. Flicker is the sensation experienced by the human vision when fast changes occur in the intensity of light sources, leading to premature eye strain, eye irritability, physiological discomfort, physical and psychological tiredness, and even pathological effects as photosensitive epilepsy. This phenomenon is provoked by supply voltage fluctuations due to high power loads such as arc furnaces or large motor drives at starting point that draw fluctuating current. This phenomenon is due to the fluctuating quasi-steady state of non-periodic voltages and currents with a modulating frequency, which is the frequency of the fluctuation. This waveform can be decomposed by the Fourier transform in a sum of the DC term, the fundamental component of the waveform, the sinusoidal waveforms of frequencies multiple of the fundamental frequency, which are harmonics, the non-integral waveforms of the fundamental frequency, which are the interharmonics, and the interharmonics below the fundamental frequency, which are the subharmonics. So, flicker is produced by the light oscillations due to the subharmonics of frequency below 30 Hz, which are not detected by the human eye. These subharmonics appear when the modulation frequency is below 30 Hz. There are two indexes for the measurement of flicker severity. The short-term flicker severity index, which is measured in 10-minute intervals, and the long-term flicker severity index, which is an average value of the 12 short-term flicker severity indexes measured in 2-hour intervals. The standards fix the limits of these indexes to measure the effect of flicker on people.